Welcome to Section 5, Lesson 6. In the previous lesson, we composed two functions to chain operations into pipelines. Today, we cover a special case of composition, the inverse function. The inverse of a function f, written f to the negative 1 or f inverse, is the function that undoes f. If f maps an input x to an output y, then f inverse maps that output y back to the original input x. Composing f and f inverse in either order gives the identity function that returns the input unchanged. Inverse functions are the natural undo operations across all of mathematics, science, and computing, and they appear constantly in encryption, decryption, decoding, and many other reverse the process applications. First idea on the board. The inverse function f to the negative 1 undoes f in the sense that f composed with f inverse and f inverse composed with f are both equal to the identity function. Composing them either way returns the input unchanged. F of f inverse of x equals x and f inverse of f of x equals x for every x in the appropriate domain. This identity on composition property is the defining feature of the inverse and is the test you use to verify any candidate inverse function. The procedure for finding the inverse of a function f is the swap and solve method. Step 1, write lie equals f of x. Step 2, swap the roles of x and y, replacing y with x and x with lie. Step 3, solve the resulting equation for I in terms of x. The new expression for y is the inverse function f inverse. The procedure works for any function whose inverse exists, and the algebra in Step 3 uses the standard inverse operation techniques from Section 3. Not every function has an inverse. For the inverse to exist as a function, the original f must be 1 to 1, meaning each output is produced by exactly one input. If two different inputs produce the same output, then the inverse cannot be a function because the same input would map to two different outputs. The horizontal line test on the graph of f decides 1 to 1ness f is 1 to 1 if and only if every horizontal line crosses the graph of f at most once. Functions that fail the horizontal line test are not invertible as functions over the full domain, but can sometimes be made invertible by restricting the domain to a subset where the test passes. The inverse function f to the negative 1 is the function that undoes f. Composing f and f inverse in either order gives the identity function f of f inverse of x equals x and f inverse of f of x equals x for every x in the appropriate domain. This identity on composition property is the defining feature of the inverse. Here is the swap and solve procedure for finding the inverse algebraically. Step 1 is to replace f of x with y, writing y equals the rule. Step 2 is to swap x and y everywhere in the equation. Step 3 is to solve the new equation for y in terms of x. The result of step 3 is the rule for the inverse function f to the negative 1 of x. Step 1 in the workflow, write y equals f of x. If f of x equals 2x plus 5, then write y equals 2x plus 5. The variable y stands in for f of x to make the upcoming swap step visually clean. Step 2. Swap x and y throughout the equation. The equation y equals 2x plus 5 becomes x equals 2y plus 5 after the swap. Every appearance of x is replaced by y and every appearance of y is replaced by x. This is the geometric step that reflects the function across the line y equals x. Step 3. Solve the swapped equation for y. From x equals 2y plus 5, subtract 5 from both sides to get x minus 5 equals 2y, then divide by 2 to get y equals the quantity x minus 5 over 2. The expression on the right is the inverse function rule f to the negative 1 of x equals the quantity x minus 5 over 2. Verify by composing f of inverse of x equals 2 times the quantity x minus 5 over 2 plus 5 equals x minus 5 plus 5 equals x. The composition produces the identity, confirming the inverse. Here is the first worked example. Find the inverse of f of x equals 2x plus 5 and verify by composition. Step 1. Write y equals f of x, y equals 2x plus 5. Step 2. Swap x and y, x equals 2y plus 5. The original input variable becomes y, and the original output variable becomes x. This is the structural step that flips the function. Step 3. Solve for subtract 5 from both sides. Minus 5 equals 2y. Divide both sides by 2. Y equals the quantity x minus 5 all over 2. So f to the negative 1 of x equals x minus 5 over 2. Step 4. Verify by composing f with f inverse. F inverse of x equals 2 times the quantity x minus 5 over 2 plus 5. The 2 and the divided by 2 cancel, leaving x minus 5 plus 5, which equals x. The composition equals the identity, so the inverse is verified. Step 5. Verify the other direction by composing f inverse with f inverse of f of x equals f inverse of 2x plus 5 equals the quantity 2x plus 5 minus 5 over 2 equals 2x over 2 equals x. Same identity result. Both compositions return the input unchanged, confirming f inverse is the correct inverse function. Step 6. Sanity check by trying a specific input. Fluff 3 equals 2 times 3 plus 5 equals 11. Now apply f inverse to 11. The f inverse of 11 equals 11 minus 5 over 2 equals 6 over 2 equals 3. The original input 3 is recovered exactly as the inverse should do. So inverse of x equals x minus 5 over 2. The big lesson from this example is the swap and solve procedure applied cleanly to a linear function. Linear functions are always 1 to 1 if the slope is non-zero, so they always have inverses, and the inverse of a linear function is itself a linear function with reciprocal slope. The pattern slope may goes to slope 1 over m, intercept b goes to negative b over m. Memorize the pattern for linear functions and the inverse computation becomes a quick lookup for the rest of the course. Here is the second worked example. Find the inverse of f of x equals x squared plus 1 with the domain restricted to x greater than or equal to 0. The domain restriction is essential because x squared by itself is not 1 to 1 over all real numbers. Restricting to non-negative x makes f 1 to 1 and inverse able. Step 1. Verify the 1 to 1 property on the restricted domain. With x greater than or equal to 0, f of x equals x squared plus 1 is strictly increasing because squaring increases as x increases through non-negative values. Strictly increasing functions are always 1 to 1, so the horizontal line test passes and the inverse exists. Step 2. Apply the swap and solve procedure. Write y equals x squared plus 1, swaps, and ix equals y squared plus 1. Step 3. Solve for y. Subtract 1 from both sides. X minus 1 equals y squared. Take the square root of both sides. Y equals plus or minus the square root of x minus 1. Two solutions in general, but the original domain restriction said the original x was non-negative, which means the inverse output y must be non-negative because y equals the original x. So we take the positive square root only. Step 4. Inverse of x equals the positive square root of x minus 1. The domain of the inverse is x greater than or equal to 1 because the radicand x minus 1 must be non-negative. The range of the inverse is y greater than or equal to 0, matching the restricted domain of the original f. The domain and range swap between f and f inverse in general. Step 5. Verify by composing f of f inverse of x equals the quantity square root of x minus 1 squared plus 1 equals x minus 1 plus 1 equals x. Identity verified. Step 6. Sanity check. F 2 equals 4 plus 1 equals 5. F inverse of 5 equals the square root of 5 minus 1 equals the square root of 4 equals 2. Original input 2 recovered. So inverse of x equals the positive square root of x minus 1. The big lesson from this example is the domain restriction craft move. Functions that fail the horizontal line test over their natural domain can sometimes be made invertible by restricting the domain to a subset where the test passes. The squared functions, absolute value functions, and many trig functions all use this restriction trick to define partial inverses. Always check the 1 to 1 property before computing an inverse and restrict the domain explicitly if needed. 3 mistakes that catch every algebra student during their first weeks of inverse function work. Each one is fixable with a small explicit habit applied on every problem. First mistake, reading the inverse notation f to the negative 1 as 1 over f. The notation looks like a negative 1 exponent, which would normally mean the reciprocal, but in function context the negative 1 denotes the inverse function, not the reciprocal of the function value. F to the negative 1 of x is the function that undoes f, while 1 over f of x is the reciprocal of the function value. The two are completely different operations and produce different results. The fix is to memorize the function context meaning of the negative 1 notation inverse, not reciprocal. Second mistake, computing the inverse of a function without checking that the function is 1 to 1 over the relevant domain. A student looking at f of x equals x squared computes the inverse as plus or minus the square root, ignoring that x squared is not 1 to 1 over all real numbers and therefore does not have a true inverse function. The fix is to apply the horizontal line test before any inverse computation and to restrict the domain of f if necessary to make it 1 to 1. The restricted domain trick is standard for squared, absolute value, and trigonometric functions. Third mistake, skipping the swap step in the swap and solve procedure. A student looking at y equals 2x plus 5 solves for x directly, getting x equals y minus 5 over 2 and writes this as the inverse. The result is correct, but the variable names are wrong. The inverse should express the new output y as a function of the new input x, not the other way around. The fix is to always perform the swap step explicitly, write y equals f of x, then replace every x with y and every y with x, then solve for y. The swap is the structural step that produces the inverse rather than just an algebraic rearrangement of the original. Inverse functions are the universal undo operations across every quantitative field. Anywhere a forward operation is defined, the inverse operation that recovers the original input is also useful, often essential. 4 broad sectors below. In encryption and decryption, the decryption function is the inverse of the encryption function. The encryption applies a forward transformation that scrambles the plaintext into ciphertext, and decryption applies the inverse transformation to recover the plaintext. Modern cryptography relies on encryption functions whose forward direction is fast and whose inverse direction is computationally hard for an attacker without the key, while being fast for the legitimate recipient with the key. The whole field is built on careful function inverse design. In algebra and calculus, the logarithm function is the inverse of the exponential function. Log base a of x is the unique value y such that a to the y equals x. The logarithm exponential inverse pair is foundational across all of higher mathematics, especially in calculus where the derivative of log x has a clean closed form because log is the inverse of xp. Section 13 of this course covers the logarithm exponential pair in detail, building on today's inverse function concept. In trigonometry and calculus, the inverse trigonometric functions arcsine, arccosine, arctangent invert the sine, cosine, and tangent on appropriately restricted domains. The trig functions are not 1 to 1 over their natural domains because they are periodic, but restricting to specific intervals like negative pi over 2 to pi over 2 for sine makes them 1 to 1 and inverse able. The inverse trig functions are essential for solving trigonometric equations and for computing angles from coordinate or geometric inputs. In programming, every undo operation in a text editor, image editor, or version control system is essentially an inverse function. The forward operation modifies the document state in some way, and the undo operation applies the inverse modification to restore the previous state. Keeping a clean separation between forward operations and their inverses is a core software engineering pattern. The mathematical inverse function concept is the foundation that programmers borrow continuously. 3 things to take with you from this lesson today. Inverse functions are the universal undo operations across all of mathematics and computing, and the swap and solve procedure plus the 1 to 1 diagnostic are the core craft skills for inverse work. First, the inverse function f to the negative 1 is the function that undoes f. Composing them in either order gives the identity function f of f inverse of x equals x and f inverse of f of x equals x for every x in the appropriate domain. This identity on composition property is the defining feature of the inverse and is the verification test for any candidate inverse. Second, to find the inverse algebraically, use the swap and solve procedure. Write y equals f of x, swap x and y throughout the equation, then solve for y. The resulting expression is f to the negative 1 of x. The swap step is essential and structural. Skipping it produces an algebraic rearrangement rather than a true inverse function. The procedure works for any 1-to-1 function and uses the standard inverse operation techniques from section 3. Third, the horizontal line test decides whether a function is 1-to-1 and therefore has an inverse function over its natural domain. The graph of f passes the test if every horizontal line crosses it at most once. Functions that fail the test can often be made invertible by restricting the domain to a subset where the test does pass. The squared, absolute value, and trigonometric functions all use this domain restriction trick to define partial inverses. Always check the 1-to-1 property before computing an inverse and restrict the domain explicitly when necessary. The inverse function concept is foundational to all of section 13 on logarithms and exponentials, where the logarithm is the inverse of the exponential function, and to inverse trigonometric functions in later courses. Coming up next, the lesson called piecewise and step functions, where a single function rule is built from several different rules applied on different sub-intervals of the input domain. Piecewise functions broaden the function concept to cover many real-world quantities that change behavior at threshold values like tax brackets, shipping rate tiers, and step cost pricing.